Nuclear power is one of the options for carbon-free power, and it's particularly interesting because it can be used in baseload mode, and then with some clever engineering, perhaps it can also become more dispatchable into the future. So to talk about this, we have two fantastic people. The first of them is James Ellis, Jr., who's a retired admiral in the U.S. Navy and former commander of the U.S. Strategic Command. In this role, he was responsible for the global command and control of the U.S. strategic and space forces, reporting directly to the Secretary of Defense. He retired from the Navy in 2004 after 39 years of service. During his career, he completed Navy nuclear power training and was qualified for the operation and maintenance of naval nuclear propulsion plants. Admiral Ellis is also currently the Annenberg Distinguished Visiting Fellow at Stanford's Hoover Institution, where he serves on the Shultz-Stephenson Energy Policy Task Force. In 2012, he retired as the president and chief executive officer of the Institute for Nuclear Power Operations, which is a very interesting organization that brings together the industry to self-regulate. Amongst many other things he's done, in 2009, he completed 3 years of service as a presidential appointee on the Intelligence Advisory Board. He's also a graduate of the U.S. Naval Academy, the Navy Pilot School, and Navy Weapons Fighter School, also known as Top Gun, so we have a Top Gun with us today. Anyway, he has many other accomplishments, and I can't think of a better person to join us in this discussion. And I'd just like to briefly introduce, again, the second participant in this session, our own George Schultz, who's a distinguished fellow at the Hoover Institution and chair of the Shultz-Stephenson Task Force on Energy Policy. He has served in the Reagan administration as chairman of the President's Economic Advisory Board and as Secretary of State. He's from New York City, or New York, we won't hold that against him. He went to Princeton University, where he graduated a year before my father, I finally figured out. And so he was appointed by President Nixon as Secretary of Labor in 1969, Director of the Office of Management and Budget in 1970, and Secretary of Treasury in 1972. He went on then to be the president of the Bechtel Group, and has then joined the Hoover Institution in 1989. So we have a very distinguished group of speakers who will join us. And right now, I would like to invite Admiral Ellis to make some remarks.
Well, thank you, Sally. And given a choice of the two CVs, I think I'd take George Schultz's any day. But I want to thank Sally, and I want to thank all of you for your continuing involvement in what I now understand has been retitled the Stanford Global Clean Energy Project, and appropriately so. How can one not be inspired by the opportunity that GCEP offers to help address the grand challenge of this century, supplying energy to meet the changing needs of a growing world population in a way that protects the environment? All of us, whether we came late to this quest or have spent our entire career striving to meet those needs and delivering on that promise, know that the single most important factor in shaping the present and defining the future is leadership. You are those leaders, past, present, and certainly future. And I thank you for that personal commitment. While we come from many disciplines and focus on a number of disparate technologies, we are drawn together by the awareness of the importance and the urgency of the need. We often focus appropriately on the environmental concerns voiced in the GCEP premise, but there is another equally important imperative: the link between energy generation and societal well-being. In other fora, I often take a moment to remind the audience that the electricity most of our neighbors take for granted, that they assume comes from flipping a switch on the wall, is actually a precious and enabling commodity unavailable to fully 20% of the population of the Earth. The CIA fact book notes the linear relationship between electricity and prosperity at the low end of the economic spectrum. If you want to take the per capita GDP of your country from $100 a year to $1,000, you must increase electricity production by a factor of 10. That explains why China has built the largest hydroelectric plant in the world, has 25 nuclear reactors under construction, and is starting up a 600-megawatt coal-fired electric power plant every 10 days for the next 10 years. It is worth reminding ourselves that, though we are involved in research, development, investment, manufacturing, deployment, and operation of energy sources that can and do generate electricity, we are producing a product that has literally created the modern world and whose successful growth can and must bring that health and prosperity to the 1/5 of the world now deprived of its benefits. The energy landscape in the United States has been reshaped since the development of our commercial nuclear power fleet. Innovations in horizontal drilling and hydraulic fracturing of shale rock have made this country the Saudi Arabia of natural gas by reimagining the production of resources once thought unexploitable. Wind and solar power dot the landscape, driven by supporting policy, but also by continuous advancements in technological performance, manufacturing, and business strategy. They have evolved from science experiments to now justifying their own roles in our changing electric grids. Meanwhile, rethinking how we use our energy, from LED lighting to low heat loss windows, has dramatically improved efficiency and disrupted the curve on national electricity demand. Over the past decades, nuclear power has been an affordable, reliable, and low-polluting pillar of our energy system. As we look to the future, can it too be reinvented to sustain and enhance the nuclear contribution to a newly diverse and robust energy industrial landscape? By way of background, less knowledgeable audiences than this are often surprised to learn that we have 99 commercial nuclear reactors in this country, producing 20% of our nation's electricity, fully 33% of the world's nuclear power, and about 2/3 of our nation's emission-free electricity generation. This number does not include the 100 naval nuclear reactors that continue to power our Navy's submarines and aircraft carriers over 60 years after USS Nautilus first put to sea. The number of commercial nuclear reactors in the United States has recently declined, as 5 have been shut down in the last 3 years for ultimately economic, not safety reasons. That electricity generation reduction will be more than offset by 4 units under construction in Georgia and South Carolina, and 1 reactor being completed by the Tennessee Valley Authority. Globally, the overall trend in reactor construction is dramatically up, with 67 reactors under construction around the world, even as Japan continues to restart a portion of its fleet in the wake of the Fukushima events, and Germany attempts to exit the commercial nuclear electricity industry by transitioning to gas, renewables, and coal. Our purpose in the Shultz-Stephenson Task Force on Energy Policy's Reinventing Nuclear Power project is to offer a technically grounded and policy-informed assessment of the case for a U.S. civilian nuclear power future in a modernizing grid. To do this, we have asked experts from around the country to use a fresh mind to identify the largest obstacles to shaping national energy policies in this area and the decision points around them, to specify potential roles for government, military, and the private sector, and finally to propose solutions in defining a way forward. As we begin, we are focusing on one new and thought-provoking approach to nuclear power: small modular reactors, or so-called SMRs, a number of designs for which have been created over the last decade, fully 31 around the world at last count. SMRs are technically defined as producing less than 300 megawatts of electricity, less than 1/3 of the amount produced by today's average commercial plant, and could be used singly or in groupings tailored to meet local electricity demands. These concepts, some scaled-down versions of existing plants and some employing new technologies, are intended to produce significant advantages in scale, cost, safety, distributed power, reduced waste, security, and industrial space expansion, while also bringing the historic benefits of commercial nuclear power. As Sally has mentioned, emissions-free baseload generation, power source diversity, and energy security. At the same time, progress towards licensing, production, and employment of this technology has been slow, and potential commercial introduction remains years away. To that end, the following areas merit consideration. First, the need. In light of America's energy transformation, especially natural gas's increased use in power generation, is there still a business case for small modular reactors? What are the emissions implications of, on the one hand, coal-fired electric generating plants being replaced by natural gas generation, while on the other hand, older conventional nuclear plants are closed or age out in large numbers in the 2 decades ahead? And how might SMRs fit into the potential security implications of a grid with an otherwise declining share of long-lived, fuel delivery secure baseload capacity? Secondly, the impact of regulation on the nuclear industry is significant. While essential to ensuring public safety, the processes led by the Nuclear Regulatory Commission, which guide the design, certification, site approval, granting of a combined construction permit and operating license, and oversight of operations, have been complex, laborious, lengthy, and expensive. Application of NRC oversight to SMR designs and operation will unavoidably shape the business case and determine to a significant degree the practicality of the SMR concept. What about potential customers? In the United States, economic market forces are preferred to long-term government subsidies. In the regulated market, SMR construction and operation must pass the review of states' public utility commissions in order to allow pass-through costs. In the unregulated market, they must compete with low-cost gas generation. What is the future of the commercial nuclear enterprise in the United States in general, and for SMRs specifically? Are there niche markets such as remote locations, military bases, and critical infrastructure where SMRs and their distributed generation might play a significant role? And what is an appropriate role for government in supporting accelerated research and development and proof of concept testing? An oft-stated justification for advancing a program of SMRs is to retain or revitalize the industrial base. Components for the current and projected fleet of large nuclear reactors can no longer be produced domestically as a result of the elimination of large forging manufacturing capability in the United States. All reactor vessels and steam generators for reactors currently planned or under construction in the United States, for example, are produced abroad. Proponents of SMRs note that their significantly smaller size would be a good match for current U.S. industrial capacity. Is this a realistic possibility? And if so, what does the industrial base need in order to step up to the task, and who will provide it? A final and important area worth exploring is the ability of the United States to influence global policies and standards in the commercial nuclear enterprise. With only 4 new-build reactors under construction in this country, some worry that our ability to shape global construction practices, operational safety standards, and counterproliferation policies will inevitably decline. They note the lack of a standalone U.S. nuclear reactor supplier to compete in a growing global market. Is this a real concern, and if so, what can be done about it? If the U.S. regulatory process, overseen by the NRC, is the world's gold standard, is the dramatic increase in the number of commercial reactors under construction outside the United States a cause for real global concern? In this reshaped energy landscape, and as Washington grapples with proposed climate and environmental regulations or subsidies that will, de facto, shape our country's power sector, underlying technologies continue to advance. During this unexpected period of energy abundance, we believe it is important to carefully and collaboratively create a long-term, deliberate U.S. energy strategy and fully understand what role nuclear power could or should play in it. Key areas of exploration include the role and importance of nuclear energy in meeting current and future environmental goals. How do the realities change in the alternative futures of either increasing or decreasing nuclear power contributions to the national energy mix? Does the climate math work out without nuclear, existing or new, is a fair question. If we look out 10 to 20 years, is there a Plan B generation portfolio apart from intermittent wind and solar, plus natural gas and some hydroelectric power when climatologically available? Though there has been progress thanks to the efforts of many in this room, the promises of carbon capture at size and grid-scale electricity storage have not yet delivered. Does this influence the urgency for nuclear power? The U.S. is just a portion of global greenhouse gas emissions, so it's useful to think about how the policies we adopt here can have the most global influence. Many climate policies talk about what we will or will not do domestically, but driving down the cost and commercializing a viable, scalable, zero-carbon technology like new nuclear could help domestically and have larger global impacts too. U.S. electricity demand, as we all know, is now essentially flat. But the International Energy Agency estimates that global power generation will increase by 80% through 2040, with $21 trillion in new investment. China was the one to use early U.S. technologies to scale up production and drive down the cost of solar energy, which the whole world now benefits from. Could the U.S. be the one to do that for small modular reactors? Is this our comparative advantage globally? Capital, technology, industrial supply chain, systems integration, regulatory frameworks, security, all historic American strengths are needed. As Ken Caldera here at Stanford has noted, when renewables are expensive, people want to find ways to bring costs down. But when nuclear is expensive, people see cost as a reason to reject the technology. The process we have begun, and indeed the creation of a national energy policy that we hope it will inform, are critically important. The character and tone of the discussion and debate must be worthy of the gravity of the issue. It seems to me that the process, if it is all that it should be, can be described in just two words: insight and integrity. My Webster's Unabridged Dictionary defines insight as penetrating mental vision or discernment, the faculty of seeing into the inner character or underlying truth. Insight is not opinion, snap judgment, conventional wisdom, or impressions, and true insight can be extremely difficult to obtain. In fact, many great men have publicly offered their insights and predicted the future of their industries with varying and checkered degrees of success. For example, in 1945, the Dean of Engineering at the Massachusetts Institute of Technology scoffed at the idea of a rocket that would travel as far as 3,000 miles. He went on to say, "Technically, I don't think anyone in the world knows how to do such a thing, and I feel confident that it will not be done for a very long time to come." Just 12 years later, in 1957, the first Air Force missile wing was activated and the space race was on. And just 12 years after that, men walked on the moon. The technology that allowed much of the world to witness that lunar landing was also the topic of a pessimistic prediction. David Sarnoff, general manager of RCA in 1955, predicted, "Television will never be a medium of entertainment." Come to think of it, given today's reality show programming, his insight may have been more accurate than we give him credit for. Another technology that we today take for granted was predicted never to flourish. As many of you are aware, Ken Olson, who was then president, chairman, and founder of Digital Equipment Corporation, said in 1977 that there is absolutely no reason anyone would want a computer in their home. Even for the genius of Albert Einstein, forecasting was a tricky business. In 1932, Einstein said, "There is not the slightest indication that nuclear energy will ever be obtainable." Fortunately for the nuclear industry, Einstein was a bit off the mark on that one. But seriously, history has made us thankful for the visionaries of every era who prove assumptions wrong, conventional wisdom far too conventional and not at all wise, and promptly set out to do the impossible. They sought true insight, that penetrating discernment and underlying truth, and may it be always so. The second of the two words that have shaped my thoughts in these remarks is integrity. Admittedly, it can be difficult to talk about integrity without preaching, and I will try to talk about it in simple and a forthright way that acknowledges integrity has always been a part of our scientific, academic, corporate, and governmental processes when they are at their best. It was Senator Alan Simpson who once said, "If you have integrity, nothing else matters. If you don't have integrity, nothing else matters." It seems to me that the energy discussion and debate must be removed from the stovepiped and singular either-or context to genuine collaborative and complementary considerations. In engineering terms, it cries for a systems approach, uniting all elements and accounting for how their contributions will affect outcomes over time. In truth, there is likely no single answer, and shouting past each other, uneven comparisons, or demonizing those of differing views ill serves the dialogue. We cannot allow the debate to polarize and divide at a time when the challenge is great and the need is urgent. In an effort to be bipartisan, I think it was Senator Daniel Patrick Moynihan who said, "Everyone is entitled to his own opinion, but not to his own facts." Integrity is still about openness and honesty and the ability to have those crucial conversations and, yes, crucial confrontations that must be a part of this continuing journey. These are but a few of the issues that must be considered in an energy policy process that includes not only GCEP and all of you, but countless others. But this opportunity is fleeting, and in the comfort of our newfound energy security, we may be tempted to delay and defer decisions that, even if taken today, will be decades in the execution. As Benjamin Franklin said, "You may delay, time will not." If our country is truly serious about reducing carbon emissions from the power generation sector, we cannot give up prematurely on nuclear power. This nearly zero carbon-emitting source of electricity faces some serious long-term challenges, but its environmental benefits are unparalleled. It is the largest scale source of electric generation without significant carbon emissions. And in the words of former Energy Secretary Steve Chu, if we want to make a serious dent in carbon dioxide emissions, not to mention having cleaner air and cleaner water, then nuclear power has to be on the table. His successor, Ernie Moniz, who was with us last Friday, noted, "A more productive approach to developing nuclear power and confronting the mounting risks of climate change is long overdue." Why settle for trading coal for natural gas and renewables when you could have nuclear, natural gas, and renewables, diversifying the energy portfolio and helping to keep the grid reliable? Natural gas is often termed a bridge technology. The question is, a bridge to what? Why be satisfied with a 50% reduction in emissions when you could potentially get to near zero? These questions must be less rhetorical and more real as we work to shape and not merely react to the demands of the future. As Exelon Corporation's John Rowe once noted, nuclear is a business, not a religion. And unlike articles of faith, the market requires constant reinvention to stay relevant. Ultimately, objective merits should determine how and if nuclear power is able to fulfill its full promise. U.S. leadership in developing and fostering a global civilian nuclear power ecosystem over the past half-century is undeniable. In this new energy landscape, we must fairly assess if the American nuclear enterprise can build on this precedent to legitimately reinvent itself for the next. Thank you.
Excellent. Well, thank you for that absolutely marvelous talk about reinventing nuclear power. The way this session will work is I'm going to sort of probe some specific aspects of nuclear power for about 10 minutes. We'll have a guided discussion. Then we'll open it up to all of your questions. So there'll be plenty of time for that. As a way of starting, Admiral Ellis, I was wondering if you could say a little bit more about small modular reactors and what are some of the benefits that they would achieve in terms of reliability, cost, safety, security, and so forth, in comparison to the sort of traditional, nuclear fleet that we know today.
Well, thanks, Sally. And again, I want to emphasize up front, I'm not selling anything. I'm here to talk about questions that need to be answered, and I think I laid out a significant range of those in my remarks. The designs that are out there fall largely into four areas. There are some that are old designs, essentially small versions of pressurized water reactors that we have had in existence for a number of years. There are emerging new technologies that represent pebble bed and others that are focused on enhanced safety and the other elements that are important to nuclear plants. And then there's the forward-looking piece. There are designs out there, liquid salt, for example, molten salt, that essentially are 95% efficiency, effectively consuming their own waste and transmuting the actinides and dramatically reducing the level of ultimately spent fuel or waste that would have to be dealt with. And there's finally things that they term almost like nuclear batteries that in a hub and spoke mechanism are sealed, cannot be opened, proliferation resistant, that could be operated and then retained back to a central, perhaps government or private sector repository. There's a full range of technologies here. As I mentioned in my remarks, parenthetically, there are 31 designs available around the globe, but they're fundamentally designed to deal with all of the issues that confront nuclear energy and have for decades. And first of those is cost. That has to be dealt with. The safety issue has got to be paramount. The spent fuel realities, and I call it that because under the current reactor fleet, 95% of the energy is still in that fuel when it's removed from the reactors after third burn, and a number of nations, not us, around the world reprocess that in order to have access to it. And then the final thing that you have to deal with ultimately is public acceptance. But public acceptance in the final analysis is in many ways related to those first three. So these designs, and they're in academia, they're in the private sector, some are VC funded, are of growing interest, and these are the options that could be explored going forward.
Okay, so just to follow up a little bit, if we look back 5 years ago, what you would commonly hear is nuclear power is the low-cost backstop option and so forth. But fast forward to 2014, 2015, and now what we hear is nuclear plants are just too expensive. So if you accept the premise that there's a lot of benefits to having nuclear power in the mix, what do you think can be done to try to deal with this cost issue, to lower the cost? What partnerships with government, industry, and so forth?
Well, as you would imagine, there are a number of models out there, and some of them are under consideration, as some of the national labs are talking about co-sponsoring an enterprise, or even the Tennessee Valley Authority and Bonneville Power in Energy Northwest has begun to explore some of those options. So I think all those things are in the realm of the possible. But you hit on the key issue here. Absent an economic demand, and given the low cost of natural gas, the private sector is understandably, since most are publicly traded utilities, unwilling to invest what Department of Energy estimates would be $1 to $2 billion in proof of concept on some of these technologies. And so the question is, do we want that as a hedge? Do we want to have that capability, given the developmental process that would have to unfold and the alternative futures that could confront us? Would we want a reliable, as you described it, baseload, load-following capability, all of which could be delivered if these designs are successful? And if we want that as a hedge, how do we prepare the groundwork for that and begin to advance to a prototyping phase, which can then validate not just the technology, but the manufacturing costs, the regulatory oversight and the price that's paid for that, and all of the other entities. And of course, you can't argue with the inherent safety, since most of these designs are compartmentalized, containerized, modular means. In many cases, all of the components are inside, and at least in concept, though they've not yet been proven, would be an order of magnitude or two safer than current plants, which are already at a fairly high level.
Okay, well, thanks. So the next topic I'd like to bring up has to do with another objection to using nuclear power, particularly if we imagine that, the use of nuclear power expands dramatically around the world. There's the risk of proliferation of nuclear weapons. And Secretary Schultz, I was wondering if you could speak to that issue of proliferation. What are the risks? How do we contain it?
It's happening. And I think a huge threat to the world is the possible use. It doesn't take many nuclear weapons to have a global impact. So I think it's something we need to focus on very quickly. And I was interested in Jim, as he was outlining different possibilities, as one that consumes its own waste. So that would seem like something less likely to cause proliferation. But I think it's a huge problem.
So are you confident that there are measures that could be put in place today, institutionally, cooperatively amongst countries to try to manage this issue? Do you have some specific suggestions for, the reality is that, we just heard, 57 plants in China. There are more, how do we, what are some specific concrete actions we could take to help address this issue?
Right now, there's hardly anything going on. That's one of the problems.
No.
The most promising thing is something that President Obama started, I think, about 4 years ago. He had a meeting of heads of government in Washington. There's since been one in Korea and one in the Netherlands, and there's a fourth one coming up. And the idea is to see how we can get better control of fissile material, which of course is a key. But I would hope, and I've been pushing people to say, can we use that fourth one to create a kind of nuclear enterprise that would work on the question of nuclear weapons and their proliferation? But you've got lots of dangers.
Yeah. Would you like to?
I certainly would, Sally. I was at the summit in Korea, as a matter of fact, the nuclear security summit that the president chartered, and clearly there's a lot of concern, and appropriately so, about all of that. But as is often the case, there's a lack of effective mechanisms, as the secretary has noted. The IAEA, interestingly enough, 90% of its budget goes to counterproliferation issues. Only about 6% goes to commercial nuclear safety issues. So they're, in terms of people and resources, they're focused on it, but about 10 years ago, they explored whether they could become more of an enforcement, oversight, regulatory body globally, and quite frankly, that did not get much traction. And so I'm afraid the bilateral approach that the secretary did so well when he was in government is something that has to be explored more fully. And I do think that a level of conversation at the national level is going to be very, very important, because the implications of loose nukes or fissile material and the like will ultimately impact us all. But on the other hand, in fairness, there are 4 nations at least in the world that reprocess, and I visited the reprocessing plant that the French operate in Le Hague, which, by the way, is U.S. technology, which we sold them in the 60s. And I asked them, how do you deal with a nearly pure stream of plutonium? Their answer, somewhat simplistically, and perhaps it was mistranslated, was, well, we guard it. And so the fact of the matter is that a security regime has to have some of the integrity I talked about as well, and a lot of personal buy-in and commitment at the national level.
So do you think the U.S. should revisit its policy? So we have a policy that says we won't do any reprocessing, or that's the de facto standard today. Do you think we should revisit that as a way of rethinking how do we deal with the nuclear waste issue? Well,
actually, it's interesting. I was doing some research a couple of weeks ago prior to going to Washington for an event that Hoover was sponsoring there, and while we're all familiar with the policy that was established in 1976 by President Carter, that the U.S. would not pursue reprocessing because he was concerned about the proliferation risk, most elements of that were relaxed in 1981 under the Reagan administration. And so, it's still a national policy, but the question then is, how do you build an infrastructure for that? The expense of reprocessing. We don't have a shortage of uranium. We do have issues, I think, with spent fuel that are going to have to be considered over the long term, storage and the like, as we reset the effort that the federal government was pursuing at Yucca Mountain. It's going to take a while to build that consensus-based approach again, as they talk about it. And so what are we going to do in the meantime? But reprocessing isn't cheap. It requires a different level of infrastructure, a different type of chemical separation and the like. And while we've had a little bit of that experience on the military side, we have no experience, nor, quite frankly, the incentive to do that in the private sector.
Okay, yeah, I'd like to open it up to questions now. So please start thinking. Okay, well, how about Amory? Could we have a mic up here so people could hear the questions? That'd be terrific.
Amory will give us the answers.
I'll just speak up. I have two questions.
Oh, no, bring the mic.
I think you need the mic.
Yeah, you need the mic.
I have two questions that are essentially about economics. The first is, as a matter of physics, reactors don't scale down well. That's why we make them big. So the hope is that SMRs would gain economies of mass production. But then you're face to face with another kind of SMR, small modular renewables, which scale down very well and are decades ahead in exploiting their formidable economies of mass production. That's why they beat gas today. So I'm wondering what makes you think that SMRs could overcome the several-fold cost disadvantage of today's fission reactors against renewables. My second question is about opportunity cost. New build nuclear as we know it would be about 3 or 4 times costlier than modern unsubsidized renewables, whose grid integration, as I described yesterday, have been resolved. But that means if you buy a new reactor, you're getting several times less carbon saving per dollar than if you bought the renewables, and about 10 to 40 times less than if you bought efficiency instead. So if you don't buy the most climate effective, that is most carbon saved per dollar options, aren't you reducing and retarding climate protection by not getting the most carbon saving per dollar that you could get? Thank you.
Well, on the scalable piece, I think, I'm not the physicist, but clearly the fact that there's 30 plus designs going around the world, there's, I think, a number of them are being fully supported by the academic complex and the like. I do believe that their pursuit of that kind of argues that, hey, the physics is in the realm of the possible, and particularly when you start talking, new designs, and so traveling wave and the molten salt, these kinds of things, and I think the costs have to be tested. I think that's why I believe that you've got to do a proof of concept. Does it really work, and does it scale? But clearly the early ones, the smaller versions of pressurized water reactors, the physics are fairly well modelable, and those have been demonstrated. The high end, the higher ones, the transmuting the waste and things that Bill Gates and others have been funding and supporting, they have to be built and they have to be proven. And I think that's a fair question to ask, and I think it's something that, as I said, we need to decide as a nation how we're going to resource, depending on the alternative future. How do these costs come out? How do you do the base load generation? How do you create an infrastructure that is really a systems approach to all of this, and what role could these advanced technologies play? Are all questions that I think as a nation we've got a little bit of a hiatus in order to begin to answer. Not a lot, so I think we need to move forward on that. Now, in terms of the intricacies of the costing model that you described, there are other costs involved, as you know fully well in nuclear, and quite frankly, we avoid a 500 million metric tons of pollutants into the air every year with the current nuclear fleet. And so, there are real costs, there are the construction costs, there are the fuel costs. Nuclear reactors, for example, much higher upfront costs, capital costs, as you know, but their percentage of fuel costs compared to their generation are fractions of those compared to gas and the like. And so the question then becomes, what do you think the future of gas is going to look like? How long is this going to be there? What about the ultimate change in the emissions curve if, you know, things move more quickly than we have anticipated, and the long lead time required for the study of nuclear? So I think the question is not to try and predict exactly what these designs are going to look like, but not give up on the research and development, the understanding of the potential that it offers societally, socially, and environmentally in terms of clean electricity generation for the future. I just think it's a little too early to pick winners and losers, because I don't think we know all those answers yet.
And I'll just add something. I mean, I also think it's a little too early to say that the grid integration problem for renewables is solved. I mean, clearly there are many examples of countries, you know, integrating 50, 60, maybe extreme 70% renewables into the grid. But I think we have a long way to go before we can really conclude that we have the answer to that question. And having dispatchable baseload power with no carbon, either through carbon capture and storage or nuclear, I think has to stay on the table.
Yeah, the integration piece is something that, again, hasn't been fully tested because no one's quite frankly done it. The German model is the only one that we have that we can see is underway, and recent estimates are that it's going to cost the Germans over $1 trillion to reconfigure their grid. Now, I don't have any idea what's involved in all of that, but that involves restructuring and realigning a grid, and you can make a case that ours is older than theirs. And so how this is all going to play out, again, it calls for that systems approach that considers all the pluses and minuses fairly and openly, and then lets the chips fall where they may.
Okay, Secretary Schultz, I think you wanted
I wanted to suggest a policy way of grappling with these issues. Step one, provide sustained, adequate support for energy R&D. It turns out when you look at places like Stanford or MIT and maybe other places, I just don't know, that when there's a substantial federal program, it attracts private dollars because they want to know what's going on and they want to contribute. So you get a multiplier of maybe 3 to 1. So that's a pretty good deal. But let's have sustained support, and people know it's sustained as a necessary way of mounting the right kind of research effort. Second, let's put a substantial price on carbon and let the marketplace sort it out. And you say natural gas. Natural gas it's cheap, but it's not bearing its full cost. So they got to bear their full cost. So if you do something like that, then competitive sources, pressures will tend to find the kind of answer you need. But I think in the case of the small nuclear reactor, you've also got to have some research effort that's got to be basically subsidized by some combination of public and private.
Okay, great, thank you. Okay, questions. Okay, we'll go here and then we'll go back over there. Yep.
Would you mind commenting on waste, the waste problem, and the water cooling, assuming it's water cooled?
Mm-hmm. Two great questions, and as you know, the industry prefers the term spent fuel because, as I said earlier, even after 3 burns in current fleet of commercial nuclear reactors, 95% of the energy is still in there. Actually, Emery, correct me, it's probably 96.2%. I think it's something like that in terms of fractions, and it has to be dealt with. But increasingly, and I was with some folks from the Department of Energy in Washington last week, they acknowledge that it's going to, as they restart this process, the consensus-based process, the technical borings, the kinds of things that we're going to have to wrestle with are going to be years in delivery, regrettably, because as you know, the federal government committed to this several decades ago and has amassed a large trust fund to fund it, but has yet not delivered on that requirement. So in the interim, there are possibilities of regional storage areas and dry casks above ground, highly secure, of course. Transportation then of the spent fuel becomes a challenge, but conceptually and technically there's no reason that couldn't be done. In many ways, this is a political issue and a societal issue more than it is a technical issue. We know how to do this. The Yucca requirements, as you're aware, went from 10,000 years to 100,000 years to finally 1,000,000 years before the project was finally ended, and that's a long way. I'm probably not going to be around to see how that all plays out, and I'm not trivializing that, but there are people out there who want to consider nuclear reasonably, but are uncomfortable with an answer that says, well, trust us, we'll figure this out in 100 years, and so I think that's a fair piece. The cooling issue, they have to meet the regulatory requirements, the delta T across the cooling water, and in some cases it's forced the industry to make decisions about shutting down plant. Exelon is shutting down one, for example, because of tightened environmental regulations about the temperature difference on their once-through cooling at a nuclear power plant, and so they're going to close the plant. So we've got to meet those criteria. There's no one asking for waivers, but this is where you start building cooling towers and other technical options that don't use direct through or one-pass or two-pass river water. So there are options to deal with the cooling issue, but no one's asking for any relaxation of that regulation. You could make a case that, ironically, in kind of a large do loop, that the global warming, the temperature increases are in themselves raising the temperature of the water, and in some cases forcing some of these considerations. But it doesn't matter. The industry still needs to and intends to meet those very strict criteria.
Seawater is okay.
Yes. Yeah.
Okay, we'll take one more question and then we'll go back and we'll wrap up.
So I come from a state, Idaho, that is one of your regional storage facilities proposed, and we have nuclear waste leaching into our aquifer that feeds most of southern Idaho. So I don't see nuclear as being the lowest cost solution. We've spent $10 billion, I believe, in the last 10 years trying to clean up the waste at INL, Idaho Nuclear Lab, and we haven't even begun to clean the thing up yet. So if you take that cost and spread it out over the technology, it's not the least cost solution. And until we store the waste where it's generated, we don't have a solution, because you're just going to foist it on low population states like Idaho.
Yeah, well, again, that's the reason for the consensus based on the commercial side, but much of what you're talking about, and I proudly lived in Idaho Falls for a year and was a daily commute to the site. Most of that came from military and weapons programs, not from the commercial nuclear side, which is the element we're talking about now. The manufacturing of fuels, the process by which nuclear fuel on the commercial side is done is well overseen, well understood, lots of EPA and other oversight and the like, but that doesn't invalidate the concerns you've got, and quite frankly the folks at Hanford have as well, for how you're going to deal with the vestiges of the Cold War, and certainly that's something that has to be dealt with appropriately, and I know that that's an issue that the Department of Energy is working with, but I would differentiate that from the commercial nuclear enterprise that we're talking about today.
Well, we're being pressured to take the waste, the reprocessing waste from France and other countries, where right now our state is being pressured to take that.
Yeah, from reprocessing from France?
Yes.
I'm unaware of that. I know the French have a business model where they take in spent fuel, reprocess it, and then ship both the product, the down-blended plutonium, and the waste back to its customer. But I wasn't aware that the U.S. government was a part of that. So.
Okay, well, I think we need to wrap up, but what I'd like to, each of you to make some final remarks to sort of help as people digest this material with some final thoughts. Secretary Schultz.
Well, my main thought is, in this setting, I do better being quiet and listening to Jim Ellis, because he really knows something about it. But I do think, as we consider energy policy, we need to think about security, we need to think about the environment, and we need to think about economics all the time. And if you drop one of those, you're in trouble.
Yeah, thank you.
And my only point would be to echo the Secretary's, and that is, hey, we have an opportunity here as a nation and as a world to shape a future. We're not driven by energy crisis. We're not driven by lines at the gas pump. We've got a bit of time now to think deliberately about this, and I think an even-handed discussion, as I said, one of real insight and appropriate levels of integrity is important to helping get to that answer. But on the nuclear side, I'm always mindful of a conversation I had with Mohammed El-Baradei when he was the Director General of the International Atomic Energy Agency before he retired from that and ended up trying to bring democracy to Egypt. And he talked about the promise of nuclear energy. And he said there's actually two promises. The first promise is the promise we all talk about, Sally has, and all of us have, which is emissions-free, baseload, safe, reliable generation for the betterment of mankind. But there's a second promise. And that promise is the promise that all of us that are involved in the nuclear enterprise must make to our nations, to the world, and to ourselves, that we will do this as well and as safely as it can possibly be done. And so if nuclear is going to have a future, it's going to have to meet both of those promises.
Okay, well, thank you very much.